will be able to see streaming events. You will be able to see streaming.
Oh, okay. Yeah.
Welcome to the conference in Machine Learning and Sustainable Energy Systems. Today we will be having audience in the auditorium as well as via streaming. We are honored to be joined by Nicole Ludwig and Gwen Hirsch here that will be joining us in this conference. I'm going to read some important points about the profile of our guests. Nicole Ludwig is leading in the research group Machine Learning and in Sustainable Energy Systems within the Cluster of Excellence, Machine Learning of Science at the University of Tubinga. Is that correct? Since November in 2020. Before coming to Tübingen, she was postdoctoral researcher within Helmholtz A at Karlsruhe Institute of Technology, where she also did her PhD in computer science within the DFG Research Training Group of Energy Status Data. She has been a visiting researcher at the University of Oxford during her PhD and initially studied economics with a focus on econometrics and computer science at the University of Freiburg and the University of Oslo. Her research focuses on probabilistic machine learning for problems related to sustainability, and she's especially interested in uncertainty and relationship between weather, climate, and energy system. Her work has been awarded several Best Paper Awards from leading conferences in energy informatics. Gwen Hirsch holds a master's degree in machine learning and one in cognitive and interactive system neuroscience. Since the beginning of 2023, she is a PhD student in machine learning and sustainable energy system research group within the Cluster of Excellence, Machine Learning of Science at the University of Tübingen. Her PhD project focuses on the development of robust and flexible neural network architectures to solve time series forecasting problems within complex systems such as the energy market. Today, the lecture will last approximately 1 hour. The first 30 minutes of the presentation will be the presentation of our guests, and the rest of the time will be used for questions you may have about this conference. So without any more preamble, we welcome to our guests, and now Dr. Nicole Ludwig will be holding the presentation.
Thank you for the introduction, and nice that you're here. So I'll be talking a bit about machine learning for sustainable energy systems and basically what we are doing in my group. And hopefully you'll find this as interesting and fascinating as I do find it. You've already heard that we're from Tübingen, and it's a tiny town in Germany, so I don't think anyone has heard of it before. But so that you roughly know where it is, this is Europe, and depending on where you cut the map, Tübingen is in the heart of Europe. But it's in southern Germany. The next large town is Stuttgart, and the next known airport, I would say, is Frankfurt. But it's a really tiny town, so yeah. It's great to be in Mexico City and see what a big town looks like. Yeah, I'm going to talk about the research that I am doing and the people in my group are doing. So I just wanted to show you who's in my group. Gwen Hirsch is here with me, but the research is done jointly by the PhD students and master's students here. That's again the wrong direction, sorry. So what we care about most in the group is doing AI for sustainability, but also doing sustainable AI. And we currently mostly focus on affordable and clean energy, climate action, and sustainable cities and communities, but trying to do more that can use machine learning or AI to support the sustainable development goals. Why is that interesting? I hope I don't have to talk a lot about this slide, but basically energy on a global perspective is responsible, so how we use energy is responsible for roughly 25% of the CO2 emissions globally. It varies a bit from country to country, but on a global average, it's roughly these 25%. So all of the orange block that you can see is the CO2 that comes from the electricity system. Now, if we would shift production from fossil fuels to renewable energy sources, we could reduce a lot of that CO2. Yeah. And the problem with electricity in general is that it's not only coming up in how we produce electricity, it kind of could also come up or also comes up in, for example, the transport sector, and some of the industry uses a lot of electricity, and then how we build and how we use our heating systems and stuff like that is also related to electricity. So electricity in general is very important in this system. Now we want to get electricity from renewable energy sources, mainly solar, wind and hydropower, and there's some challenges if we want to do that. So what's the main challenge? I think you probably know, but if we look at this gray blob and think that it is the demand, then what we can do with conventional energy sources and in most countries are doing at the moment is that we follow that demand with the supply. So we supply exactly as much as we need to cover the demand, or maybe a bit more. Now, if we only have renewable energy sources, then the problem is that we can't follow that gray blob. So we can't just match the demand with our conventional energy sources. But what we have is just whatever we are given by the weather conditions of the day. So for example, the red curve might be what we have available from renewable energy at a specific point in time. Now, that gray blob, we actually know something about that. It's made up of all of the processes, and it's made up of how we use electricity. So one idea is that in the future, maybe instead of the supply following the demand, we could shift our demand around such that it fits to what is available from renewable energy sources. So kind of that, yeah, in order to match the supply from renewable energy sources, we could change how we use electricity. Now, kind of obviously, some of the things in the house we are very happy to probably shift around. I mean, at least I don't care whether my washing machine runs during the day or in the night, as long as I have clean clothes when I need them. With a coffee machine, I'm not willing to compromise that much. But in general, what we're looking at is a lot of these processes, not only in the household, but especially in industry as well, we could shift around and actually use when there's renewable energy around. And because we don't want to think about that most of the time, we can, or we want to use, for example, machine learning to help us schedule when to use which machine. But yeah, so the general challenge is that demand and supply don't match, and we have to do something about that in order to be able to use as much renewable energy sources as we can. Now, in my group, we are very interested in understanding the relationship between weather, climate, and the energy system, because that's kind of what makes it difficult to have a fully renewable energy system. It's basically just the weather. But the weather is a really chaotic and complex system, and additionally it's changing, so we have climate change. So the interactions in a renewable energy system, they're really fascinating, or we're trying to understand them better using machine learning. What we need to do a lot to understand the system and also to be able to, for example, shift when to use the washing machine in time, is we need to know what is available from renewable energy sources. So a lot of what we do is forecasting the renewable energy supply. And because the weather is chaotic and not very certain, we want to do that, or we have to do that under uncertainty, and we really care about what are we certain about, and what are we uncertain about, and what are our algorithms uncertain about. And then lastly, we want to increase the use of sustainable energy in order to mitigate climate change. But when the climate's changing, that also changes how we can use electricity from the sun, for example. In Europe, for example, the average wind speeds are supposed to decrease during climate change. So wind turbines will be less effective the worse climate change gets. And that interaction is also really interesting to learn more about. It's changing on my computer, it's not changing here. Now it is. If it's now jumping around a lot, that's because I've been jumping around a lot with it. So there's lots of things where we can use machine learning and help, hopefully, to integrate more renewable energy systems or build an energy system that is as sustainable as we can or want to have it. Some of the projects, I brought some of the projects and just want to talk a bit about what we're doing. So one of the projects that I'm going to focus on a bit more in a couple of minutes is we try to do some intelligent control and especially fault detection in solar thermal systems. I've learned today that solar thermal systems are actually quite popular or used a lot in Mexico, which is great. They're not used much in Germany, for example, but they're really, really nice and efficient and a clean way to use heating and hot water. But they're also very faulty very often. And you don't really want to have an engineer going to the system every month. So we are looking into how we can automatically detect the faults. I've talked about the shifting around of the processes that either you use or an industry partner would use in order to better match the supply from renewable energy systems. And as we also don't want to do that by hand and check the forecasts and then figure out when to use the washing machine, we are looking into agent-based systems and especially reinforcement learning to automate that for us. And one other application that we're looking into using machine learning is power system analysis for transmission grids. So the transmission grid is the long distance grid of the electricity networks. It's always the highest voltage and sort of the grid where the electricity travels the long distances. And depending on the country, we currently only have data from Europe, India, and some parts in Africa. But we're trying to analyze these systems and like where should you build new connections in that transmission grid, or where should you put very large power plants such that you can optimally distribute the electricity every point in time. And because they're really complex and large systems, we hope that machine learning can help because it can deal with very large and complex systems and lots of data. Yeah, I've already talked about forecasting and the fact that we are interested in uncertainty. So we always care not just about the middle of these lines, but also like how certain or uncertain are we about that forecast. And this, for example, is a very typical demand curve. In this case, it's from London, but it looks very similar across Europe, at least. So if you have a peak in the morning where people go to work, and then there's a little bit during the day, and then you have another peak in the evening when people come back from work. Yeah, one of the main challenges with machine learning is that it's purely data-driven most of the time. So anything we already know about the system, it's really hard to feed that into the neural network and tell the machine learning algorithm, hey, we already know a lot. Could you use that information to learn more? So Gwen's PhD topic is on including like statistical and physical information in machine learning. Especially with energy systems, they're engineered, so we know exactly what we've put into them. We don't need machine learning to learn that, but machine learning can focus on other things if we are able to put that information in. We're currently not able, but hopefully we will be in the future. And then lastly, what I already talked about, the impact of climate change on renewable energy systems. And there we are very interested in, especially like the very local climate change. So a specific wind turbine, for example, if we put up a wind turbine today, it's gonna experience a change in climate. So we need to know how it's gonna perform under these changing climate conditions. Okay, that was the overview. And I'm gonna dive deep into some of the topics, and you don't have to understand all of it. But if you already know a bit about machine learning, then maybe you can take away something from here. So this is a solar thermal system as they look like with our industry partner, at least. There are these collectors that just heat up water, and then that can be used for heating or just warm water usage. And this is how a typical day should look like. And whenever it doesn't look like that, there's going to be some fault. And I've just, for example, in this installation fault, there was just 2 sensors were basically just switched. And then the whole system did not do what it was supposed to do. But the people living in that house with that system did not realize for a couple of months, because there's backup and a backup energy from there's some backup energy. So you don't realize, because you still have energy, you still have hot water, you still have heating, but the solar thermal system is just not doing anything. But if you analyze the data, you realize. And also here, there was just, so it should not get, the collector should not get this hot.
I'm sorry, am I allowed to ask a question?
Sure.
I got just a little bit lost over here. So this household
Mm-hmm.
thought they were using clean energy, but they weren't.
Basically, yes,
They
yeah.
were actually fooled into thinking they were.
Yeah, because the sensors were switched, they were just using, I think in this case, the backup was gas, and they were just using the gas and did not realize for a couple of months that the solar thermal system isn't doing anything. Yeah. But that was so yeah, we kind of want to prevent that from happening, obviously. And we hope that with an automated system that should get detected very easily. Now we train a form of neural network, a variational autoencoder, to kind of learn what is the correct behavior. So we train this network to be able to reconstruct what a correct behavior should look like. And then whenever our network isn't able to reconstruct what has been happening, we say this is a fault. It's work in progress, but it's already, these are actually old numbers. We've already managed to update that a bit, and it's now working quite well in the sense that it can detect faults without knowing what types of faults there are around. So we don't have to feed it the information that, oh, there can be a parameter fault and there can be switched sensors, but it can just look at the data and be like, this does not look normal, and then put out, this isn't normal. And then still someone has to check what's going on, but at least you get a flag as in something isn't right. Yeah. Another challenge, or the main challenge with renewable energy systems, are that they're weather driven, which means whatever the weather is doing influences to 100% what the renewable energy system is able to do. Which means that we kind of need to know something about the weather. Now, there exist weather models, so numerical weather models for the whole globe, put out by lots and lots of different organizations. NASA is one that puts out weather forecasts. In Europe, there's also an equivalent that puts out weather forecasts. And what they basically do is they, for the whole globe, have a grid everywhere and put out information for each of these grid points. And then you get some form of a map, for example. Also, the maps you probably see on TV are usually fueled by some form of weather model. Now, these weather models would be perfect if we could measure the state of the atmosphere at any given point in time and space. Unfortunately, we can't. We only have a very selected few weather stations around the world, and especially the higher atmospheres. You've probably heard about the incident. I think China had this stratosphere balloon that got taken down by the US. But these balloons are actually mostly used for weather monitoring. So they get put up into the stratosphere, which is like the second layer when you start counting from where we are, and measure the state of the atmosphere. And then that gets fed into these models. Yeah, but as we can't measure every point in space and time, what we get out of these models are like possible trajectories. So we kind of make a very educated guess what the state of the atmosphere currently is, and then run these physical models. And then they put out what, for example, the temperature could be like for the next 6 days. So that's the temperature in Kelvin. That's why it's so high. And each of these lines is equally likely to happen. So when we are at this day, we don't know where we're going to end up in 6 days. That's also, if you check your weather app, the next day it's pretty good, and then 6 or 7 days ahead it's not that good. And that's the reason why, because there's so much uncertainty. But if we want to do forecasting, then we kind of have to acknowledge that uncertainty. So we have to use that information in the weather data together with maybe some technical information from the wind turbine if we do wind power forecasting, and then put out a forecast that also reflects that uncertainty from the weather, and probably additionally the uncertainty that the algorithm that we're using here brings in. Now, one of the questions we asked ourselves was like, if we have a wind farm, in this case somewhere in France, then what information is relevant from us, from these? I said there's like a grid for the whole globe of weather information, but what information do we actually need if we want to know the wind power of that single wind farm? So we used a rather complex neural network that used these weather maps, so information of that map, and then historical time series data from the wind turbine.
The other one, you said one about neural network. Did you say that you fed kind of information? I didn't understand.
What we feed in here?
Yeah.
So this one type of information is the weather map. So the information about the weather at all of these grid points. And the other information is time series data from the wind turbine. So the wind turbines, they record depends on a turbine, 5 minutes, 10 minutes. They record what's happening within the turbine. And we have that data together with the weather data. We feed that into 2 different networks in this case, and then have a third network combining that information. Yeah, and what we were interested in is kind of what information is relevant. So we tried out kind of, yeah, we call them donuts, but they're not round, but like square donuts. And then all of the diagonal axes, and to figure out what do we actually, what information do we actually need? Because using that whole map is very data intensive and very computationally expensive. So we want to reduce the features that we use as much as possible. And yeah, in this case, the 3x3 grid, so one that was not exactly at the wind turbine, but very closely surrounding the wind turbine, that was the best we could use. And another thing that was really important was actually using that information from the wind turbine, because that was very useful whenever the wind turbine was out due to maintenance or something. So we could already see that in the turbine data and then make more useful predictions. In that case, just predict 0 instead of something, because we know the turbine isn't working. Yeah, and overall that actually worked very nicely. And we tested that with several turbines that formed a very small wind park in France. Yeah, the third project I brought with, and I want to talk about a bit more, is like the climate change impact on renewable energy systems. I'm pretty sure you've seen some form graphic like this before. Just it got really hot. It's actually quite old, as in like there was a 2020 temperature anomaly, but you can already see that at least over Europe the temperature increased, but that's the same for every continent. And there's already been some studies looking at what happens to different renewable energy sources in 2015 or 2050 or 2100, but on a very broad scale. So the information they put out was for, there's like just very few data points for each of the continents and countries. Now, the reason why there are only these very few data points is that what we get out of the climate models is a map like this, for example. And not sure you can see it, but there are very fine grid lines throughout the world. And we only have information, for these grids. If we zoom into, in this case, Germany, we can see what that grid looks like for a specific country. And you can see that, for example, this is one of the states. This is the state where Tübingen is in. And for that state, we basically have just, not even 9 data points, more like 3 data points. So 3 wind speeds. Now, if we have a specific wind turbine somewhere here, like an aggregate of, that's just not going to tell us much. Because if we have a wind turbine somewhere here and a wind turbine somewhere down there, they get the same wind speed, which is completely unrealistic. Because if we look at the map from today, then there's much more happening in that map. And for example, here that dark blue part, that's actually a mountain range. So we know that there's a mountain range and that the weather is different in that mountain range. So our aim is to put some of that information into the climate model. Now, the climate models are so coarse because it's so computationally expensive to calculate them. And you have to use already several supercomputers and server farms to calculate these climate models. And so we're trying to do the rest with hopefully machine learning. So what we're aiming to do is called downscaling. So we go from a global scale to down to a local scale. And basically, instead of having that coarse grid, put like a very fine grid into into each of these grid cells. Why do we think we can do that? Because we know the weather. The weather is described by physical equations, so we know what's going on. And we want to model the weather in these grid cells given the climate boundary conditions from the climate model. So we want to model the dynamics in the grid cells using explicit physical knowledge of the atmosphere. You don't have to understand that, but that's roughly how this information looks like. It's a partial differential equation, and there's lots of them, at least 4, but they're usually described by more. And the tricky part is the Navier-Stokes equations. Which we even theoretically, there's still a lot of things we don't know about Navier-Stokes equations, but we know that they describe the weather. And one of the things we're currently working on is how we can get these explicit PDEs into machine learning. We do that with something called Gaussian processes. Usually they are just fitted to data points. So you create a set of functions, and then whenever you have a data point, at this point, the process gets conditioned to fitting that data point. And instead of just fitting data points, we tell explicitly that there's a specific PDE that this Gaussian process has to fit. And with very simple PDEs, that actually works. So with a simple heat equation, we can already, within one of these grid cells, kind of create patterns that make sense. And that's sort of what we aim to do with the real weather equations as well, but we're not there yet. So at the moment, we're focusing on affordable and clean energy, sustainable cities and communities, and climate action, and trying to use machine learning to get closer to these goals. And one thing I did not talk about a lot, but what we do care about is that we want to use as little computational resources as possible, because it would make no sense at all to have a very complex machine learning model that takes up a lot of energy to reduce only very little energy. So that is also a concern. That is also a concern, which is, to be honest, in machine learning is not a thing a lot of people care about, because we've already earlier talked about ChatGPT that uses up a whole lot of resources, but we aim to use as little resources as possible to actually contribute to these goals. And if you are interested in joining us for the next 3 days, we have a workshop where you can do some specific coding with energy data and try out some neural networks and reinforcement learning yourself. Thank you.
Thank you all, and we would like to invite you to, if you have any questions, we will be pleased to answer. And only I want to ask you to ask the question in English, please. Thank you.
My Spanish is not good enough for Spanish, so I'm sorry.
My English is not good either. But is the only way to evaluate wind power is with the use of turbines, or can you use any other kind of tools to evaluate it? Did I explain myself?
So do you want to know whether you can just forecast wind power when you have a wind turbine already, or?
Because I understand. I understand that you were using wind turbines to evaluate wind power, right?
Yeah.
But can you use any other tools to evaluate wind power in a bigger area or more spaces?
Yeah, you can, there's like wind power curves for every turbine that is around, but they're specific to the turbine. But if you just want to know whether a specific area would be good for a wind turbine, you could so you could use the given curve or the given equation to transform wind speed to wind power. So you don't necessarily need a wind turbine to get to wind power or to know about the wind power in an area, but it's way more accurate, because the real wind power that you're going to have will depend on the specification of that turbine. But yeah, if you're just interested in is that area theoretically useful, then you can use some of the standard curves and equations that are around.
Yeah, thank you. And I have one more question.
Sure.
When you say that the sensors fail so much in the solar heaters, wouldn't it be easier and less resource
Yeah.
if you change the sensors? Like if you develop yourself in the sensors in place of studying them?
Yeah, so that heavily depends on the faults. Sometimes the sensor is faulty, but what happens more often that the person installing the system does something wrong, and then better sensors wouldn't really help. But yeah, having good sensors is really, really great, but they're also really expensive. So there's sort of this trade-off between having the best sensors around and maybe having a tool that can work with semi-optimal sensors. Yeah.
My last question. If you said that you were using machine learning for energy grid allocation, right? How do you get more data, like in terrain and problems with energy installation with different terrain? How do you get that information?
Yeah, so what we currently do is take the existing transmission grid and analyze just theoretically where a line would between, if you already have two nodes, would another line there, or a thicker line, thicker not really, but like a line where more electricity can flow through, would that make sense? And whenever the optimization proposes a completely new line, then you can sort of have some cost associated with that. That's what we do. We say, okay, a line here would cost X and a line over there would cost Y. You should take that into consideration. But that's, yeah, it's heavily simplified. But yeah, the terrain and stuff, that's really important. That's true.
Hi, my name is Rodrigo. I would like to ask you about the process of feature engineering while you're applying the machine learning models. With this, I mean that I can imagine that trying to forecast the energy supply with X amount of features in that moment is different from trying right now in these days forecasting it. Are these features changing constantly, or are you trying to find robust feature engineering for machine learning that adapts to any chaotic or complex system?
That's a really good question. Yeah, we do a lot of feature engineering throughout the whole pipeline of like building up the final model. There's a set of features that we are pretty sure that we need. For demand, for example, it's very important that you know what day of the week it is and what time of day it is, because most people are very, very regular in how they behave. So if you know it's 12 a.m., then you roughly know what the electricity consumption will be like. For the supply, for solar thermal systems or for solar PV systems, we know that the sun is the most important factor that we need to care about. But as you've seen with the wind example, we don't know all of it. So we don't know, should we include all of the information that we have, or should we just include little? So we do a lot of, it's mainly trial and error, and to figure out what are the features that we need, and in the combination that they can then also capture some complex changes. Because if you have a feature that describes the time of day, and another feature that is sort of related to the time of day, then sometime then the machine learning model will learn, okay, during that time of day, this feature will mean X, but during another time of day, this feature will mean Y. But yeah, there's a lot of trying out how to best forecast it given the feature set you have.
Yeah, and I have another question. Is the memory of the time series important to forecast it? Like, or is it like, I don't know if you use a recurrent neural network for it because you care about the previous memory, or it's not, like you care about the previous memory of the time series?
Do you want to say?
You can use a recurrent neural network structure, but there are other types of neural networks nowadays that also are able to keep in mind what happened in the past, and like, because these are time series, we need to learn what happened in the past. Definitely, yes. But there's also like attention-based methods and transformers, and yes.
Okay, thank you.
Hi, I have a couple of questions. Well, I think that the model is exclusively for wind power, right?
Yeah, so in that specific case, that one model will just produce nice forecasts for wind power. If you use the exact same model on another task, it will fail completely. But I think some of the ideas that we've used in that model can also translate to other forecasting tasks.
Right. And how hard do you reckon it would be to adapt this to other energy sources, such as like solar, for example?
I think for solar, it wouldn't be too hard. One would have to do the feature engineering process again to figure out if solar also just needs that very small amount of data, or maybe needs a bit more. But the general structure of the neural network, I think you could just reuse that. The nice thing about solar is it's very, very periodical. So it theoretically is a bit easier to predict than wind power. So that's why I think it wouldn't be super challenging to transfer it to solar. If you'd have a hydro system, that would be a very different thing, I think, because rain is really hard to predict.
Right. And well, this next question is perhaps a little bit not necessarily related to the machine learning aspect of it, but how might the energy crisis that's currently happening in Europe challenge these algorithms? Or is there any way that it could affect the data being put into it?
It introduces a concept drift. It introduces a change of the underlying distribution of the data. And so you definitely have to keep that in mind and design a model that is able to adapt to things that are happening in the world, to things that happen to the system. Yes.
Yeah. So especially when you look at demand. So the demand change, people try to reduce their mainly heating consumption. But for if you would just predict the wind power output, that would not change at all, because the wind turbine is not affected at all by what the gas network is doing. But yeah, if you have the same as with data from 2020, is significantly different than data from 2019 or even from 2022, because COVID happened. So if your model is really good, then it can adapt to these changes. It will need a couple of, in this case, probably weeks to figure out what the new pattern is, and then make nice predictions again. What I see done a lot, at least in research, is that people just take out 2020 and train them on, but that's not the good way to do it. Yeah.
Right, thank you.
Hi. I don't know if you have done it or if you have given any thought about doing it. Have you tried about scaling down not only the models, I saw the grid that you were subdividing the grid into smaller grids, but also to do the same, but for energy production, to see how would be the effect for example, for microgrid production, to see if that were a more robust model than the present model of central large generation turbine farms.
So we haven't worked a lot with microgrid or small community data because it's just not out publicly, in the sense that most people don't want you recording their energy consumption. But in general, we try to at least develop these algorithms in a way that they can deal with changes in how big the grid is. For most of the wind turbine stuff, the grid doesn't matter at all. For the transmission grid, it's a bit, I think it behaves a bit different than a microgrid would. So I think you can't just translate these algorithms directly to a microgrid. We haven't done it, but it would actually be really cool to see what happens if you just put it on a microgrid. But we would have to rely on really good simulations or publicly available data.
It's just that instead of depending on one single point of large generation, you would distribute the generation in a lot of points.
Yeah, so that's
then you
definitely,
would make it more robust, the generation.
yeah, that's what we're definitely, so on a large scale, we're definitely looking at that. So like, how would you distribute the, but the transmission grid is sort of the highest voltage grid. So that's where you would feed in a large wind farm, or if you have, in my hometown, we have, it's like a whole, like a soccer field full of solar thermal system that is used for the community around. And that is also, that's on very high power. So systems like that you would see on the transmission grid. But if you put a PV system on your household rooftop, that would not show up in the transmission grid because it just happens in, like, most of the time 2 or 3 layers down.
Question: have you? Well, I recently read an article that that the wind generation, the electric generation, will change dramatically depending on the position of the wind turbines inside the wind farm. So, have you done any research to do if machine learning can help optimize where's the optimal position of each wind turbine inside the farm?
So we have not done machine learning to optimize that, but we are very aware of the fact. So if you have one wind turbine that gets sort of all the wind, and there's one directly behind that, there's going to be turbulences and wake effects, so that the wind turbine that is behind will not, that profile will look very different. And we are looking into better forecasting already existing wind farms where these effects happen, and so that it's not this, because what's often done is that instead of using the real data, you use these equations and wind, like turbine curves, to map wind speed to wind power, ignoring all of these turbulences that happen in a wind park. And one thing we are looking at is like, can machine learning learn these effects that are happening? But we haven't tried to then better place them. But I think there's lots of mathematicians doing that.
Final question. This is about opinion, actually. Do you think that this could be these techniques could help make the energy production more democratic around the world, meaning that not only countries that have access to, all this computational power to forecast what's the best place, but actually to put it into some countries that have a lot of resources, but maybe not the knowledge or the computational power to be able to take advantage of this research.
Yeah, so we really hope, and we try to publish. We publish all our work and we try to do it as much open source as possible and have all the algorithms open source code available. But I think there's still a large gap between this research algorithm and then someone actually employing it, no matter where. So yeah, that's still a gap that we're hopefully gonna be able to at least make smaller. I think one of the ideas why we were using machine learning to do the local climate modeling is that there are some finer grain climate models around for all the rich countries. So the UK has its own local climate model that doesn't have the 150 times 150 kilometer scale, but I think 10 kilometer by 10 kilometers. Germany has something like that as well, but most countries don't.
Right.
So what we hope is that one of the goals of that project is actually to be able to create some form of Google Maps for climate models, where you then can zoom into your location, and it doesn't matter where on the Earth that location is. You can zoom in, and then the algorithm in the background will give you the local climate information. And that is, I think, one of the things that at least I really hope that will make it more, just the information more accessible throughout the world. But many of the forecasting algorithms, I think there's still a lot to do to help make everything a bit more equal.
Thanks.
Well, thank you very much for all your questions. And I think I would like to thank our guests, and on behalf of the Department of Engineering Studies of Innovation and the Institute for Applied Research and Technology, I would like to give this award to our guests, Dr. Nicole Ludwig and MSc Gwen Hirsch, for their participation on this conference, and thank you all for being here.
Thanks for all your questions.
Thank you for your questions.